Okay, Assalamualaikum warahmatullahi wabarakatuh and good evening everyone.
Good evening, Dr.
Waalaikumsalam, Doctor.
Okay, how are you today?
Alhamdulillah.
Alhamdulillah.
Alhamdulillah. Good evening, Ivan. Okay, thank you, Amar Kamal. All right. So I believe last week we already complete for the chapter 2, which is the mathematical modeling, and the last part is signal flow graph. Right. So for today we're going to start with chapter 3, okay, which is the time response. All right. So what is time response? We need to know, right? Well, we need to know what is time response. Okay. So time response is the study where we're going to study the performance of the system. Okay. And in order to study the performance of the system, we need to know how the output variable performs when we apply an input into the system. Okay. So in a time response study, normally we apply a common input such as given here. Okay. This is common test input. Okay, which okay, the first one is step signal. Okay, you can see here the input is in step. Okay, so basically it starts with 0. Okay, and then at t equal to some time, let's say 2 seconds. Okay, and then the input signal change to another value. Okay, let's say 1. Okay, and it stay at 1 until the end of the time. Okay, until infinity. Okay, so this kind of input is what we call step input. Okay, so if the unit here is 1, meaning the changes applied into the signal, input signal is 1. So this is what we call as unit step input. Okay, unit step input, if the unit is 1. But if the unit is 0.5, 2, 6, 10, 100, okay, that is what we call as step input. Okay, sometimes you may also see the x-axis is time. Okay, and the y-axis is u. U normally represent the input signal. Okay, so maybe you have something like this. Start at 0. Okay, this is also unit step input. Okay, or something like this. Okay, the shape is step, so it is a step input, but the initial point is not 0. For this one, initial zero initial condition. Okay, if it start at 0, but if it start at some value, let's say here 0.5, so therefore the initial condition is not 0. It has the initial condition will be equal to 0.5. All right. That is the most common input signal that you will see in control application. Okay, for example, if you change your oven system, you have an oven, right? And then you set the oven to 180 degrees Celsius. Okay, so initially is 0, then you change the input to 180 degrees Celsius. So it becomes step input. Okay, initially it is 0, and then you change to 180. Right? So that is an example for step input. Okay. Oh, sorry. Forgot to record. Let me record this first.
know that there is a capital city that was built for billions of people but remains
All right.
practically empty.
So that is unit step input. All right. The second one is impulse input. Okay. So again, if the unit here is 1, then we call it as unit impulse input. Okay, but if the unit is not 1, then it's just a regular impulse input where the value can be anything. Okay, it can be 0.5, 0.6, can be 2, and etc. Right? But the shape of signal is the input is changing to a value, but only at that time. Okay, like you punch something, so it impulse. Or you have a mass spring damper, right? Okay, and then you pull the mass and you release the force. Okay, you pull and release. So that is an example for impulse input. Okay, if you pull the mass and you stay, you hold the force there, then it is a unit step and it is a step input. Okay, but if you pull and release, that is impulse input. Okay, okay, the third one is sinusoidal input. Okay, sinusoidal input is when the input is in a sine wave shape. So you may have U equal to A sine omega t. Okay, or A is the amplitude and omega is the frequency of the wave, right? And then we also have RAM input. Okay, RAM input is when the input is increasing with time. Okay, so you can see the input is keep increasing with time. Okay, the example for RAM input is when an aeroplane take off. Okay, so the input is increasing with time. So the aeroplane need to respond to that kind of input. Okay, so for us, in order to determine the performance of any control system, okay, we're going to apply a common input signal. Okay, it may be in form of a step input, it may be in terms of impulse input, it may be in terms of sinusoidal input, and it may be in form of RAM signal. Okay, RAM input signal. All right. So we apply a common input signal, and then we want to see how the output responds to the input, and we want to see the behavior when the time is changing. Okay, so that is what we call as time response. That's why the name is time, because it's based on time, and we want to see the response. So time response analysis. Okay, so the time response analysis for a control system consists of 2 parts. Okay, the first one is transient state. Okay, and the second one is steady state. Okay, the first part is transient, where the input may start from 0. Okay, then it will increasing and it will keep changing until it reach to a steady value. Okay, so here you can see that the output is not changing very much. It still have some small changes, but it is very small, so it consider reaching the final value. Okay, so you can see the response is steady, right? So for this part here, this is what we call as transient. Okay, dynamic. Okay, so normally the transient analysis will be represented by dynamic transfer function. Okay, a dynamic transfer function normally from the one that you derive from the ODE and etc. That one will explain the behavior of the transient state. Okay. Right? So the dynamic transfer function will explain the behavior in transient state. Okay. As for the steady state region, okay, the behavior, the value or the performance at the steady state region will be defined by the static transfer function. Okay, later from the transfer function, you'll be able to see there's a parameter that define the transient state behavior. There is also a parameter that will define the performance at the steady state region. Right? So in time response analysis, the purpose of the time response analysis is to derive the equation. Okay, to derive the equation, they're able to explain the behavior of the output when the time is increasing. Okay, so you can see as the time is increased, the behavior of output is changing. Okay, so this behavior, this curve, this graph will be explained by an equation that what we call as time response equation. Okay, so it is given by YT. This is Y the output. So Y time response equation will be in form of it is a function. It is a function in term of time. Okay, so that is the objective of this this chapter. Okay, we're going to derive the time response equation. Okay, so given a dynamic system similar to the system before this, so from the transfer function that you have derived, we're going to derive the time response equation, so that we'll be able to plot the behavior of the output in time. Okay, so based on the behavior, we'll be able to determine the performance of the system. Okay, all right. Okay. Okay, so basically, in order to derive the time response equation, right, there are a few steps that we're going to follow. Okay, the first step is to produce the ODE equation of the model. ODE model. Okay, ODE is ordinary differential equation for the system. Okay, so the first step is to produce the ODE model, right? The second one is to transform the equation into Laplace form. Okay, so ODE model, we're going to transform the ODE into Laplace. We're going to transform into Laplace equation. All right. The third one is to apply the initial condition. If there is any initial condition or parameters or etc., we're going to apply into the Laplace equation, right? Then after that, we're going to apply the input signal. Okay, so if you are using unit step input. Okay, so we're going to apply a step signal in Laplace. Okay, if it is RAM, so we're going to use the signal in Laplace form, right? Okay, so once we apply the input signal, the fifth step is to do partial fraction decomposition. Right, so we're going to transform the Laplace equation into partial fraction function. Okay, we're going to separate the equation into the partial fraction. All right. So after in the partial fraction decomposition, we're going to solve for parameters. Solve for okay, there will be a parameter in partial fraction that we need to solve. Okay, so we're going to solve for the parameters. Okay, you may use Reminder theorem. Okay, we're going to discuss on Reminder theorem after this. All right, and last step is to inverse the Laplace. Laplace equation lah kan. Laplace equation. So so we get YT. Okay, Laplace form is in S, YS. So we inverse, we get YT. All right. So the step is you already familiar with this step. Okay. Because you already learned this step in ODE. Okay, there is a subject named ODE, so you have learned in ODE subject, or you have learned about Laplace, how to transform a function into Laplace equation, apply initial condition. Okay, maybe there is no applying input signal because this is the application for the control system. Okay. So we're going to apply the input signal. But basically, in ODE, they give you ODE, you need to transform into Laplace. So you have learned that. Okay. Apply initial condition, you also have learned that. Partial fraction decomposition, you also have learned about how to convert from a function into partial fraction equation. All right. And also for inversing Laplace equation. Okay, I believe you're already familiar with all these steps. Okay, except now we are going to apply in form of a control system. Okay. All right. So this is the first step. Okay. To produce the ODE model, mathematical model, ordinary differential equation model for a dynamic system, for a control system. All right. Okay, so now okay, this is the general ODE equation. Okay. So the general ODE equation we can see here. We're going to separate. Okay, you can see here. At this part, all the term here is output. Okay, we're going to separate the output term to one side and the input term to one side. You can see here, this is the input term. Right? So Y is the output. U is the input. Right, so we separate any part that contain output term, we will separate into one side, okay, and then any function with input term will be separate into one part. Okay, so that is basically the general equation for ODE. Right. Other than that, we also see that we're going to arrange the equation based on the order of the meaning for the output part, the highest order will be the first term. Okay. For example, maybe you have you notice here D. Okay. dn per dt n. Okay. This is also equivalent to dn. Okay, because d per dt is differential operation. So we replace with d. D is the differential operation. Alright. So we can simplify this equation because it's easier to write capital D as compared to write d over dt. Alright. So we can arrange the equation to be, let's say, y plus a1 a1 brother because for a3 lah, a3 d3y, okay, plus a2 d2y plus a1 d dy, okay, plus a0 y, okay, equal to, let's say du plus maybe adalah b plus b0u. Okay, so in general, normally we arrange the term, the highest order will be first. Okay, so you can see it is 4, 3, 2, 1 and 0. Okay, this is 1 and the last one is d0. Alright, and then of course we're going to have initial condition. Okay, so any term that contain t equal to 0. So this one here meaning t equal to 0 because the function is yt, right? So since t equal to 0, so we write y0. So this explains this is the initial condition at t equal to 0. Okay, so you also may have y prime 0, which is represent this one dy over dt. Okay, sometimes we use d operational, sometimes we can also use y prime, y single prime, y. Or sometimes you also see y double dot, y dot, y. This is the same, which is explaining second differentiation. Okay, double dot is second differentiation. Single dot is first differentiation. Okay. All right. Okay, so that is the explanation about ODE. Okay, but basically you already know how to produce an ODE equation. Okay, for example, here we have a system. Okay, we have a system, a spring damper system. Okay, the input is xi, the output is x naught. Okay, input, output. Okay, so we can write the ODE equation based on the mass equation. So we have here, let's say you draw the free body diagram, M, right? And then from the analysis, you get the direction will be Fs, Fd equal to Md. Okay, so you're going to have the equation Fs plus F damper is equal to md square x naught. Okay, so x naught is the output. All right, and then we replace Fs with the equation, which is k xi minus x naught. Okay, the equation for Fd is cd xi minus x naught equal to md square x naught. All right, so now we're going to write on in form of ODE. So we're going to separate the output to one side and the input to the other side. So the equation will become md square x naught plus cdx naught plus kx naught is equal to cdxi plus kxi. Okay, so this is our ODE, right? The output is at one side and then the input is at the other side. Okay, we separate the output term from the input term. Okay, so that is the first step to produce the ODE model, ODE equation for any dynamic system, for any dynamic system given. Okay, so that is the first step. All right. The second step is to do the Laplace transform. Okay, so Laplace transform is to transform from the time function into the Laplace function, right? So you do function in time, okay, because there is d over dt, so the function is in time. Okay, we're going to transform it into Laplace. So t will be changed into s. So s is the Laplace form, right? So in order to do the Laplace transform, the general step is to integrate from 0 to infinity and then multiply the function with exponent negative st over dt, dt. All right. So this is the general step. I believe you already learned about this step in ODE. Okay. So basically, since for the control engineering, we're not going to derive, we're just going to use. Okay, because this is application subject, we're just going to apply any function, any common function, okay, that is already derived, being derived by someone else. There will be a table there. So we this one, except we're not going to derive it, we're just going to use it. Okay, so for the Laplace transform, in order to derive, in order to transform time function into the Laplace form, okay, we're going to use this table. All right. Okay, so all right. So this is basically the input. Okay, if you have impulse input at t equal to 0. Okay, so the impulse input is warna merah pula ni. Okay, let's choose another one. Right. So at t equal to 0, then there is a impulse signal. The value is 1. Okay, because why I know the value is 1? Because it mentioned it is unit step, unit impulse. Okay, so because the word there is a unit impulse, so I know the unit is 1. Okay, so in Laplace, you're going to apply 1. Okay, so because you know, this is u t equal to 1 in time function. adalah dia punya T ni, T bigger adalah dia punya ni kan, but basically at T equal to 0. Okay, so in Laplace form, US will equal to 1. Yeah, because the unit is 1. If the UT is equal to 2, okay, so US will become 2. Okay, so it depends on the unit, how many unit at the input side. Okay. It's similar to the unit step U. Okay, so it is like that. So the unit is 1. Okay, so in Laplace form, it is 1 over S. Okay, but if the unit is equal to 2, US equal to 2, okay, in Laplace transform, it will become 2 over S. Okay, if the unit is 10, it becomes 10 over S. Okay. All right, and then we have RAM input. Okay, RAM input, it is 1 over S square. Okay, because it is unit RAM input. So unit RAM input meaning the gradient here is 1. Okay, that is unit RAM input. Okay, so if the gradient is different, then it will have, let's say, 2 over S square. All right, okay. Other than that, this is common function. Meaning we will going to see this term, this function a lot in control system. Okay, because the control system will very much relate to this kind of exponent, sine wave, cosine wave, damp sine wave, and damp cosine wave. Okay, so okay, so this is a common function. All right. Okay, for this part here, okay, this is we're going to use this part when we're going to transform the ODE. Because in ODE, the term that contained in ODE is actually the differentiation, whether it is first differentiation, second differentiation, or higher order differentiation. Higher order can be 3, 4, 5, 20, and etc. Okay. All right, so basically we're going to focus to this part, okay, for the first differentiation and second differentiation, because for our course here, we're just going to focus up until second differentiation. Okay, so we can see for the first differentiation, okay, for example, you have CD. D is first differentiation, right? CDY lah. Okay, so in Laplace, it will become C multiply with S ys minus y0. Okay, y0 is the initial condition. Similar to the second differentiation, you have md square. Okay, so you have m multiply with s square md square y. Let's say md square x naught. Okay, so s x naught s minus s x naught 0 minus x naught prime 0. Okay, so any second differentiation or first differentiation term will be converted into Laplace using this function here. Right, and this is for higher order. All right. Okay, so let's see the example. Okay, let's see the example here. Okay. All right. For the example here, you need to to find the time response. Okay, meaning we're going to do all the berapa tadi? Six steps. Okay, from the ODE up until inverse Laplace until we get the time response. Okay, the system given is the spring damper system. Okay, so the analysis done on the system is we consider that the force here, okay, macam ni? Okay, so basically the equation is Fs minus Fd is equal to 0. Okay, we consider the force at that point is equal to 0. Okay, so we replace K xi minus x naught minus CD x naught equal to 0. Okay, as for the damper, it only relate to the xi. Okay, only one side change with xi, the other side is the wall. Okay, so that's why it's only contain x naught. Okay, so then we separate output with the input. So we have CD x naught plus K x naught is equal to KXI. Okay, so only to separate output term with the input term. All right. So this is the first step. Produce ODE. Right, so we already produced the ODE. Second step is to Laplace transform. To transform the ODE into Laplace form. Transform. Right. So here we can see there is the first differentiation. Okay, only the first differentiation there. Right. So therefore, we're going to have C multiply with S x naught S, refer to the table, minus x naught 0. Alright, and then plus with K x naught S, okay, because K here is in time function, so in Laplace it just in S form, x naught S equal to KXIS. Okay, okay, so this is the Laplace form. All right, then the third step is to apply initial condition. Okay, so we're going to apply the initial condition. Right, again we're also going to apply all the parameters given there. Okay, so K is 1, C is 1, so this one is 1, K is 1, K is 1. Then it's also mentioned that the initial state x naught 0 is equal to 0. Okay, therefore this term will become 0. Okay. Right, so after we apply, the equation will be left with S naught 0 S naught 0 S plus S naught S equal to XIS. Alright, SIS is the input. Alright, then before we can apply let's just write it here. 4 is to apply the input signal. Okay, so we're going to apply the input signal. So before we can apply the input signal, we have to write the equation in form of output equal to transfer function multiplied with the input. Okay, so therefore we write we factor s not s here. S plus 1 is equal to SIS. Okay. S not s output is equal to the transfer function 1 over s plus 1 multiplied with the input SIS. Okay. So we're going to apply the input signal, where the input signal SIS is equal to 1 over s. Okay, 1 over s. Why 1 over s? Okay, because it mentioned here it is a unit step input. Okay, unit step input. So meaning the unit is 1. Okay, so step input is 1 over s. So the input signal is 1 over s. Okay, therefore the equation will become 1 over s plus 1 multiplied with 1 over s. All right, so now let's do the fifth step. Okay, the fifth step is to do partial fraction. Okay, partial fraction decomposition. All right. Later I will share. Okay, basically, for the partial fraction, we get 1 over s plus 1 multiplied with 1 over s is equal to a over, let's say a over s plus b over s plus 1. Okay. So this is the partial fraction. Basically, I'm going to share you the table. Control. Ini 17 78. Okay, if you refer to the WhatsApp, okay, if you refer to WhatsApp, I just shared to you a table that is for partial fraction. Okay, form of rational function. Okay, meaning a common function. Then how the partial fraction will look like. Okay, so our function here, it is similar to the function number 1. Okay, so the partial fraction will become a over s plus b over s plus 1. All right, and then we're going to solve for a and b. Right, we're going to solve for a and b. Basically, I'm not going to show it here. Let me see. I'm not going to show it here. Just let's just use the value. So we have the value a equal to 1 and b is equal to 1 to minus 1. Letak kat sini. Okay, b minus 1. Okay, minus 1. All right, so therefore our s naught s is equal to 1 over s minus 1 over s plus 1. Okay, so step number 6 is inverse Laplace. Okay, so when we inverse the Laplace, x naught s will become x naught t, we equal to, okay, so we're going to refer to this table again. right? So you can see here there is 1 over s here, okay, for the unit step input. So if we inverse to the time function, it become 1. Okay, so therefore for 1 over s, it is 1. And then for the second term, this is the 1. Okay, so we have 1 over s plus 1. Okay, so therefore our alpha here is equal to 1. Okay, alpha is 1. Therefore in exponent, it becomes exponent negative t. Okay, so our function here will become 1 minus exponent negative t. Okay, so that is the time response equation for the system here, for the spring damper system, when we apply a unit step input, meaning unit step input with zero initial condition. Okay. Okay, so if you have this equation here, okay, so the equation is xt equal to 1 minus exponent negative t. Okay, so we can plot the response of the output. X naught, right? This is x naught. All right, so we can calculate a table. So let's say if t equal to 0, okay, t equal to 0, if you put into the equation x naught, you will get 0. Okay, so we start with 0. Okay, let's calculate for t equal to 1, t equal to 2, t equal to 3, t equal to 4. 0. Okay, 1, 2, 3, 4. Let's calculate for 5. Okay, can anyone give the value for t equal to 1? T equal to 1.
0.9, Doctor.
0.9. Something wrong. Let me check the solution. Balik. Tambah ke tolak ni? Tambah. Check balik B ni. B, S, cancel. S is negative 1. Negative 1, betul tu.
.6321, is it?
Yes, the answer is 0.63. So I am afraid the equation is wrong, but basically 0.632. Okay, that is the correct value. All right. How about 2?
.865.
0.86. All right. 3? 0.9.
502.
0.95.
0.95. 4?
0.98.
0.98. 5? 0.99. Okay, so if you calculate infinity, you get 1. Okay, right, so we'll be able to plot that. Okay, nak tambah ada series 1 is 1. Okay, kat sini tu 0.8 something. Just I just catch roughly. Okay, so basically it will behave something like this. Okay, so basically when the time is increasing, you get 1. Okay. All right, so so this is the function of time response. Okay, we want to get the equation that explain the behavior of the system when we apply any common input. Okay, any input lah, RAM input ke, impulse ke, sinusoidal input or etc. Okay, so by doing all the step, okay, first step ODE, second step Laplace transform, apply initial condition, apply input, do the partial fraction, and then inverse, you get the solution of the ODE, which is actually the time response that explain the behavior of the output. Right. All right. That is the first the first part. Okay. But of course, we still need to cover a few more things in the step there. Salah buat. Okay. Right. So let's do the example here. Okay. Alright, so let's do a quick step here. Alright, so the ODE. Okay, the ODE basically we have derived on the example here. Okay, that is the ODE there. Okay, we're not going to derive it again. We're just going to use that MD square S naught CDK or the plus, right? Right, so let's write here. The ODE is MD square X naught plus CD X naught plus KX naught equal to CDXI plus KXI. Right? So, in general, equation for the ODE, okay, the first term here, the first term does not contain any constant. Okay, so we need to divide by M here. We're going to divide by M, divide by M, divide by M, divide by M, divide by M. Okay, because if you refer to the general equation just now, the first term does not contain any constant, so it is 1. So that's why we divide with M. Right, so our ODE equation will become D square X naught plus C over M dx naught plus K over M X naught equal to C over M dxi plus KXI. Okay. Alright, since K over M equal to 2, C over M is equal to 3. Okay, so we're going to replace that. So this one will become 3. This one will become 2, 3, and 2. Ini ada K over M. K over M. Okay. Alright, so let's do the Laplace transform, the second step. Okay. So we're going to have S square X naught S plus S X naught 0 plus X prime not 0. Right, so that is the first term here. The second term is 3 multiply with S naught S plus X naught 0, right, plus 2 X naught S. Okay, that is for this term here, 2 X naught S. Right, then equal to 3 multiply with first differentiation for the input, which is S xis minus x prime tak ada x prime xi0, okay, plus 2 xis. Okay, so let's do the third step. Okay, we were going to apply the initial condition. It is given that x naught 0 is 0 and x dot 0 is 0, or x prime 0 is 0, right? So therefore this term will become 0, this term will become 0, this term will become 0. Alright, and then there is another one here, xi0. Okay, xi0 is also considered 0 because the input is mentioned unit step input. Okay, so unit step input, the common shape is okay, the common shape is like this. Okay, so it starts with 0. At 0 is equal to 0, xi0. Okay, it will start at 0. Or maybe you have input signal like this. Maybe you have, okay, this is still, this is not at 0 equal to 0. Okay, but for this example, we consider common step input with 0 initial condition. Okay, so therefore we also consider xi0 equal to 0. Okay, so now let's write the full equation. Right, so we have x squared x naught s plus 3s x naught s, okay, plus 2 x naught s equal to 3s xis plus 2 xis. Okay, so we're going to apply the input, but first let's write the equation in form of output equal to transfer function multiplied with the input. Alright, so we're going to factor x naught s here. S squared plus 3s plus 2 will equal to 3s plus 2 multiply with xis. Okay, so we're going to have x naught s is equal to 3s plus 2 divided by we can factor s squared plus 3s plus 2 can be factorized. So we have s plus 1, s plus 2. Okay, s plus 2. Okay, multiply with xis. Okay, so xis is equal to 1 over s. So therefore, x naught s is equal to 3s plus 2 divided by s multiply with s plus 1 multiply with s plus 2. Okay, so that is the Laplace form for the system after we apply the input. Right? Okay, then we do the partial fraction. Okay, let's do the partial fraction. So this form, if you refer to the table, okay, if you refer to the table that I shared in the WhatsApp, this is also the first function. Okay, so therefore we're going to write 3s plus 2 over s plus 1 S plus 2 is equal to A over S plus B over S plus 1 plus C over S plus 2. Okay, so we need to solve for A, B, and C. Okay, so we're going to solve for A, B, and C. Alright, so basically we're going to use a reminder theorem. Alright, so I think let's stop here because for reminder theorem, there is a few more steps that we're going to see. Okay, so we already past 5 o'clock. Okay, so we're going to continue with reminder theorem tomorrow. Okay. Alright, so let's stop here. If you have any question, you can ask. If you want to leave, you can also leave. Alright. So thank you. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor.
Waalaikumsalam.